So, Sayan, yeah, let's start.
Thank you, Herant, again for inviting me here. I think it's wonderful to be part of the event, and also my first time in Armenia. So really excited, both to interact as well as see the country and the city. I'll get started, and as Herant mentioned, we'll see how. It has been a relatively recent area to discover algorithms automatically using LLMs. I think the area started around 2023 or so. I mean, there's a slide at the end where I'll just kind of give you a slice of the landscape so that if you are interested, you can work on that area. So it's a relatively recent area, and our goal here is, if there are hard problems, by hard I mean typically NP hard over here, can LLMs come up with good heuristics to solve them? That is essentially the problem that we are trying to look at. Most of the talk will be focused on a particular specific algorithm, but in general, the paradigm can be broadened to cover many other algorithms, and we'll sort of end the discussion towards that. I'll get started, and again, I'm okay with having questions in between the talk. It's a 1-hour talk, so I don't want to lose anyone early and then bore you for the rest of the hour, right? So if you have any questions, feel free to interject. Just raise your hand and ask a question. I would be happy to sort of interact during the talk rather than just taking questions at the end. Okay. Right, so I think the motivation, I mean, this is the motivation for most of my research, that a lot of data is modeled as graphs. Some of the prominent examples, for example, molecules, as Heran said, atom-atom interactions, and similarly, a few other such data sets that come on the same paradigm. One is materials. I think there is a talk on material discovery also as part of the conference, probably tomorrow, I think. And then protein structures. Again, you can model them at the level of amino acids, or you can model them at the level of atoms. And then, recommendation systems, financial transactions, quite a bit of work on graphs in the vision domain as well, on modeling the interaction between various semantic structures, like scene graphs, for example, right? So there are two people talking to each other in a street, and so on. Also, every time you're using a Google map or anything of that sort, you're working on a road network, which is graph. And finally, neural networks themselves are actually graphs. And recently, there has been a bunch of graph theory-based works on identifying or interpreting neural networks. So graphs as a data model is very, very popular, and it's going to stay forever. How you process graphs can change. Lately, it has been graph neural networks, for example, and we may change to something else, maybe LLMs. But graphs as a data model, that is going to stay. So now, because so much of the data is modeled as graphs, a very fundamental operation when you're working with graphs is that how do you compare graphs? How do you say that two graphs, whether they are similar or whether they're different, right? It's a very simple. We have L2 or LP distances for regular high-dimensional data points. How do you now generalize them for graphs? So why do you want to do that, right? Yeah. So a graph isomorphism, isomorphism, yes. So isomorphism here, so the question is, by similarity, do I mean graph isomorphism? So isomorphism tells you whether two graphs are identical or not identical. And distance function is an extension of that. It not only tells you when they're non-identical, it should be able to tell you how much they are non-identical. Right? So that's where the distances come into the picture, right? Again, I am great that there are questions already coming, and I'll be happy to take more questions. Right. So why do you want to compare graphs? There are many applications, right? But this is just one application, again, motivated from drug discovery. So suppose you have a database of graphs. This could be molecules, for example, right? in a molecule, every atom is a node, and the atom-atom bonds are the edges, right? And then you have a query graph, and you want to identify which are the structures or molecules in this database that are very similar to this given query graph, right? So this is typically what we call a range query or a k-nearest neighbor query. And you can do similar things for materials, protein structures, and many other things. Often, similar structure translates to similar functions. There are layers to it, but this is a simplification. But generally, you would associate function with similarity in structures or topology, right? So these are, this is a very common query that you do in the space of graphs. Now, so there are many distance functions in the domain of graphs. One of the most powerful distance function in the domain of graph is called graph edit distance. Okay. Many of us have worked with string edit distance. We often use that to teach dynamic programming or introduction to programming in general. So graph edit distance can be interpreted as an extension of that in the space of topology. So what happens over here? Let's take a walk through an example. So suppose you are given two graphs. This is graph G1, and this is graph G2. Edit distance means what is the number of operations, the minimum number of operations that I need to make G1 isomorphic to G2. What is graph isomorphism? They are identical. So two graphs are identical. Okay. So how many edits do I need to make to G1 so that it becomes identical to G2? Okay. That is essentially the problem. What is an edit? Edit can be insertion of nodes or edges. Similarly, deletions of nodes or edges. Or you can simply do a label substitution. So if the graph is labeled, for example, if it's a molecule, the labels would denote the type of atom it is, carbon, oxygen, and so on. The edge labels could denote the bond order, right? Double bond, single bond, and you can have many such other labels as well to capture stereochemistry or any other kind of features, right? So now, if you look at these two graphs, the one possible way to convert G1 into G2 is that first you do a label substitution. Okay? So here you are changing the label E to a label A. Okay? And then you are inserting an edge over here. So you are, so from this node C here, you are adding another edge to a new node labeled E. Okay? So how many edits are we doing here? 3 edits. One label substitution, one node insertion, and then one edge insertion, right? So this is graph edit distance. A very simple operation. It's very easy to explain. We could explain that and just discuss this in 1 minute, perhaps. But it turns out that if you want to now find out what is the minimum set of edits that you need to conduct to convert one graph into the other, this is a fairly hard problem. And let us try to understand why this is a hard problem. So how do you compute graph edit distance? So suppose you are given 2 graphs, okay? So the first thing is, the first operation is, you make the 2 graphs of identical number of nodes. Okay, that's the first thing. How do you do that? So here G1 has 3 nodes, whereas G2 has 4 nodes. What I do is, first I insert a dummy node, or an empty node. That's what you can call it, which is this particular one over here. Once I've inserted this node, now they both have the same number of nodes. I want to compute a bijection. What do I mean by bijection? A one-to-one mapping from nodes in graph 1 to nodes in graph 2. Okay? So one such mapping is shown over here. There can be many other mappings. So here, for example, this node A is mapped to this node A, but I could have mapped this node A to this particular node B. I have the independence, I have the freedom to do that. So this is one such mapping, and once you have identified a particular mapping, what you do is you compute the distance corresponding to that particular mapping. So let's say this particular so let's say this particular mapping here is some mapping phi, right? So the distance for that is the distance between the node in graph G1, which is V, to its corresponding node in graph G2. Okay? And similarly, you take each edge in the first graph, let's say G1, and the distance of this edge to the corresponding edge in graph G2. Okay? What is this distance? The simple way to talk about this distance is that if the node that it has been mapped to, if they share the same label, then the distance is 0. Like a carbon node mapped to a carbon node, it is 0. But if I map a carbon node to an oxygen node, then the distance is 1. Okay? And similarly, the same thing, sorry, it's automatically progressing. I'm trying to stop that. And similarly, you can do the same thing for edges also. So if two edges have the same label, then you say that the distance is 0. If the two edges have a different label, then you say that the distance is 1. Of course, you have the freedom to say, OK, mapping a chlorine to a fluorine is perhaps a better operation than mapping chlorine to something like a hydrogen or an atom that is of significantly different chemical properties, right? You could do that. You don't have to operate in the distance of 0 or 1. You can use any other distance function. For the simplicity, we are going to assume that every edit operation has a cost of 1, but you can use something else. Okay? So therefore, what is now graph edit distance? So this distance that we said, it is with a specific mapping phi. Now you want to compute every possible mapping that you could potentially come up with, and the graph edit distance is the distance that is the minimum across every possible mapping that one could come up with. Okay? So therefore, graph edit distance is the, consider all possible mappings to identify the one that minimizes this. Okay? And this is where the challenge comes. If you have n nodes in a graph, now we are going to insert dummy nodes, and therefore n essentially is the graph with the larger number of nodes. The number of mappings that you have to consider is n factorial. Okay? This makes the problem very, very challenging. And it is not surprising. You can, in fact, I mean, this is NP hard. This is also APX hard. It's hard to even approximate. And it's not challenging because even for the simpler problem of graph isomorphism, which is two graphs are similar or not, we still are not aware of any polynomial time algorithm to actually solve that. It's not been shown to be NP hard, but we are not aware of any polynomial time algorithm either. Right? So how do you solve this? How do you solve this particular problem, right? Graph edit distance, because it's hard, but we still need to compute distances between graphs. So that's what takes us into the domain of heuristics. What is a heuristic? You come up with some rule that I will map this node to this particular node using some particular rule. You come up with such rules, and people have studied that for years. And so this is an approximation. This is not going to be accurate, but you're OK with the approximation itself. Okay? So you work with approximations. And so far, these rules would typically be generated using, you'd study a bunch of graphs, and you'd come up with some, you would form an intuition, and based on that intuition, you would come up with this heuristics. That has been the norm. But then, people started thinking about, so this started happening maybe from 2000. I think the first paper was 2019, so around after some 2017 or 18 onwards, when neural networks started becoming very popular, particularly graph neural networks, people started thinking about, can we learn these heuristics automatically from data? Okay? So no more hand engineering of heuristics, but let us learn them automatically. So how do you do that? So here is a broad problem statement, like how one could go about doing it. So what we are going to take here is a set of problem instances. Okay? What do I mean by a set of problem instances? So you give me a graph pair, let's say graph G1, graph G2, and what is the actual distance, the ground truth distance between them? And you would, so this is like a training data, right? So you construct that over 10,000 graphs or 1 million graphs, whatever, or pairs to be specific, not just single graphs. More data, the better it is. And then I'm going to train a neural network, typically a GNN, because you're processing graphs over here, that is going to approximate the solution, and hopefully this approximate solution is going to be very, very close to the ground truth. Okay? That is the objective. So essentially, so the first paper came in 2019, so not very old, but again, 6 years is not too recent in the domain of machine learning either. So what you have here is your graph 1. Here is your graph 2. You pass them to a graph neural network. And then you get a high-dimensional embedding of each graph, G1 and G2. And then you have a particular function over here that takes the embeddings of these two graphs and then comes up with a particular scalar value. Okay? And you would want the scalar value to be very close to the true ground truth, the ground truth distance. So generally, you would optimize this using some sort of an RMSE loss or MAE loss or something of that sort. Okay? So this is the general pipeline of use of automated heuristic discovery. Okay? Now, why would you want to do that? I mean, just first of all, it's just interesting, right? Can I just come? I mean, that has been the entire ML journey, right? I mean, can I eliminate a human intervention in the pipeline? I think that's excites many of us, right? But then it also, I mean, it's useful in the sense that, one is just freedom from hand-curated design. Yeah. Mm-hmm. Right. I think, yeah, so again, just to repeat the question, the question is how do I ensure that they are optimal, right? Or how good they are. And how does it work with really large graphs? So first of all, I think, graph edit distance, it is not only NP hard, it is APX hard, which means that we are not even aware of any algorithm that gives you an answer that is provably within a particular error bound. Okay, so it's a very hard problem. So we are not really looking to solve the problem exactly. That's not what we're looking. What we're trying to do here is to come up with a distance or predict a distance that is close enough to the ground truth, okay? So, but not the exact. So there is no guarantee that this function here will tell you the exact distance. There is no such guarantee. And how do you evaluate the quality, therefore? So you just generally, just like any kind of a ML pipeline, you have a train set, a validation set, and a test set, and you are just checking empirically how close your predictions are to the ground truth, right? That is essentially what we are doing. So there is no approximation guarantee or anything of that sort, and that's a limitation. So I'll come back to it a little later. Like what are the implications of those limitations? Yeah.
I think one question is the ground truth for these laws. Mm-hmm. How do you compute it to make sure that it's reasonable, right? Because the general problem is NP hard, so you can probably do exhaustive search, but how many you can do that?
Absolutely. So that's a big part of this particular pipeline, which I will mention as an explicit limitation, right? But since you ask it, so yes, so I mean, this is the kind of the fallacy or of this. Well, I mean, one limitation, right, is that to train these models, we are trying to replace GED computation exhaustively, but we need this to train this particular model. So there is a cyclical dependency on solving an NP-hard problem. Okay, so what do you do? Typically, what we do here, I'll come to your question as well. What we typically do here is there are some. We take a particular solver. Many of them are like mixed integer programming-based solvers, something of that sort, and we give it a bunch of graph pairs. Generally, these graph pairs are not going to be very large, like 25 nodes, 50 nodes. 50 is actually very hard for them. So 25 nodes, and we give them a time limit. Let's say 10 minutes, okay? And if they're able to solve it, and generally the solvers, what they do is they don't give you the ground truth distance directly. They give you a lower bound, and they give you an upper bound. And if the lower bound is equal to the upper bound, then you know that you have fit the the true ground truth. So if it is able to get to this state where the lower bound is same as the upper bound within 10 minutes, we take that pair and we put it as part of my training set. Otherwise, we just discard that. How much time do we take? So for some of the openly available molecular data sets, we can, in some of our papers earlier, we have taken 15 days to 20 days just to prepare this ground truth data, which can be substantial. And these data sets, these molecular data sets are not very large. I'll revisit this particular limitation. So, but if you're thinking this is a limitation, yes, this is a limitation. There is no question about that. Yeah. What do you mean by dimensionality here? Uh-huh. You mean the same number of nodes? Okay. So the question is, do they have to be the same number of nodes? No, they don't have to be. It's not. So if there are certain, like the previous example where I said node mapping, that you need to make them by inserting dummy nodes. But for a GNN, that is not needed. And I'll give you a picture of why that is not needed. In fact, that's a good thing about GNNs. They can handle, if you train a GNN, it does not need to be trained on graphs of the same size. It can easily handle graphs of any sizes. So that's not a problem. Okay? So I'll give you a brief overview of how the GNNs are working over here. But why you want to do that? I mean, I hope you are convinced that, well, there are certain limitations, but if we can really nail this problem, it's just automation, right? We don't need to sort of study and build our own intuition. It will just, we'll automatically learn this heuristics. Right? And the other part, which was kind of just pointed to, the hope here is that, see, the ground truth data generation is very expensive, as I said, right? We can only generate it for very small graphs. The hope is that we'll learn them on small graphs and use them to do inference on large graphs. And inference is typically much faster, right? That is the hope. It doesn't work in practice for the neural networks. And I'll come to that later because of poor generalizability. OK. So how do you do that? As I said, so these are graph neural networks. I won't go into the details of how a graph neural network works here. I'll just give you a quick overview and how it handles graphs of different sizes. So what a graph neural network will do is that for every node in this particular graph, it would embed them into a feature space. Okay? How does it do that? It only looks at the local topology of this particular node to embed them. What do I mean by local topology? Which means that it will probably look at the 2-hop neighborhood or 1-hop neighborhood. That you can decide. So this is an explicit parameter in the number of layers you want in the graph neural network. So it would take only the L-hop neighborhood of each node and embed them into a particular feature space, right? So therefore, if your graph has, let's say, 1,000 nodes versus 100 nodes, it does not matter, because I'm only taking local decisions, which is that what is your 2-hop neighborhood? How many 2-hop neighborhoods I have to embed? That doesn't really matter. Okay? So therefore, I can actually handle graphs of arbitrary sizes. So once you have embedded them, these are node-level embeddings, right? But to compare distances between graphs, I need a graph-level embedding. So what do I do? There are many architectures here, right, to do that. This is one of our own work. So this is something that we did in 2022. So I'll just briefly sort of summarize the architecture here. But this is not the focal point. So what you are typically doing here is that here first you have the 1-hot encodings of the node labels. Like, for example, let's say carbon atom or whatever you have here. You convert that into a dense feature representation. And then you have some sort of a GNN over here. There are many GNNs that exist in the literature, graph attention networks, GCN, graph isomorphism networks, and so on. So I think in our experience, GIN works the best. And then once you have, so this gives you a node-level embedding. This does not give you a graph-level embedding, as I mentioned. So once you have this, what we do here is a pool. A pool is the aggregation of node-level embeddings to a graph-level embedding. Okay? In our case, we simply take every node and we just sum them up. So it's like a sum pool, right? There are other works in the literature that do an attention-weighted pool, right? So so this particular pooling function can be another attention-weighted neural network or something of that sort. You have the freedom to kind of design other architectures, right? So this is what we do. So we get a node-level embedding, then we do an aggregation. This aggregation can be a simple sum pool, but it can be something more involved. And then you move on from there. So once you have the graph-level embedding, you are training an MLP to predict the final, embedding of that particular graph. Okay, so this is a pooling layer, and then it goes into an MLP to get the final graph embedding over here. Okay, and then given two graphs, you pass them to another MLP to do that. Okay, so now what is this table trying to show you? The table is trying to show you, so these are all the different non-neural graph edit distance approximators that exist in the literature. Okay, and this is the neural network-based one that I just presented. So this is from 3 years back, almost, right? And what you can see here in terms of the accuracy here, right? It is clearly much better than the existing solvers, the non-neural solvers that exist in the right now. So in terms of accuracy, neural networks are fairly good. You know, they're doing a fairly good job. Okay, and at the same time, there is another advantage. They are, because of using GPU acceleration and everything else, they are way faster than this non-neural solvers, which are generally branch and bound based search heuristics and so on, right? So faster and more accurate. Of course, it seems like a happy world, right? Everything is perfect, and so. This area is promising. So here is the sort of the landscape of all neural approximators of GED. So it's not like one paper. It started in 2019, and this is VLDB 2025, which is a one of the top conferences in databases. So this just concluded, I think, last month. Not even last, I mean, just 2 weeks back. And you can still see that these papers continue to arrive, all trying to sort of push. Although I don't think this area is very relevant anymore because the improvements are becoming like epsilon improvements rather than like big ideas, but papers continue to come out. And you can see a variety of conferences, like ML conferences, vision conferences for scene graphs, pure data mining, and database conferences, as well as NeurIPS, ICML, all these other ones. OK, but let's now think about this, right? So yes, a lot of activity in this area, but the area is not perfect. There are some major pain points. What are those? We have already discussed this, right? I think you have already pointed this out, that you're trying to solve an NP-hard problem, but you need to solve that NP-hard problem itself to get the training data. This is a paradox, right? How can we get over that? Second, I said that the hope is that I will train them on small graphs and generalize them to really large graphs. This actually does not work in practice. I have the results in some of our papers. I won't show it here, but it generalizes very, very poorly. The errors really deteriorate. So what you do here in this paradigm, you have to train them for each data set separately. It does not even generalize from one molecular data set to another molecular data set that well. That's level of poor generalization, right? Which makes it very cumbersome because you're generating this NP-hard ground truth data, training this GNNs, and then you're trying to going for inference, right? Is it really worth it, right? And then finally, it's a black box, right? It works well, let's say, on the data sets that you share, but then on the unseen data sets, you have no idea like how magnificently it can do or how drastically it can fall in terms of quality, right? It's a pure black box. Second, another important part, right? When you set graph edit distance, it's not just the distance, but you also sometimes may need to know what is the mapping of nodes or what are the edits that you are doing, right? It only tells you the distance. It does not tell you the edits that map to that particular distance, right? So therefore, all these things are some of the major pain points that that remain unsolved, and it will largely remain unsolved as long as you're working with neural networks, right? I mean, they are black box by design. So what do you do here? And that takes us kind of, I took a lot of time to motivate, but I think that's kind of important here to understand the context. So this year we came up with this paper here called GRAIL. Okay, thanks, it's back. And the main change that we did, instead of discovering weights of a neural network, let us discover programs. By programs, I mean actual code that can solve this particular problem. Okay? What do I mean? Let's just understand that a little bit more. So what we are basically trying to remove the pain points. So we still need a set of problem instances, graph pairs, but I don't want any of their ground truth distance. It's NP hard to generate. Okay, so that is eliminated. That's no longer part of my training data. And second, instead of training GNN that gives me the approximate solution, we replace that with, so I will take this graph pairs, I will pass them to an actual program, right? And this program is to be discovered by us. That gives me a distance that is close enough to this particular true distance. Why is this better? The reason we believe this is better, because by program means it's completely open, right? You exactly know what logic was applied to get to this particular distance. And it will tell you exactly what the edit path is. So it makes the entire black box thing a white box, right? And an important implication, which we'll see later, is that it generalizes way better across distributions. Because when you go into the domain of programs, you are kind of forced to work at an abstract level of logical decision-making rather than mapping to a particular functional space, right? Which is more prone to overfitting. So how do we do this? So let's revisit the definition of a graph edit distance here. So what we have here, so graph edit distance, we are kind of revisiting that, is that it's a minimum, it's a distance between two graphs, and I want to find the mapping that minimizes the distance across every possible maps, right? This is the graph edit distance. Where is the root cause of the problem, the scalability problem? I have n factorial maps, where n is the size of the graph. So let us now think about whether we can do something like this, which is, suppose I don't want to consider every n factorial possible mappings. Can I come up with a much, much smaller number of mappings? Let's call them pi prime, right? So pi prime is way smaller than pi, such that if I take the minimum over pi prime, this is reasonably close to the minimum over every possible mapping. Okay? And therefore, because it is every possible mapping is equivalent to the graph at a distance itself, the whatever distance you get from here is very close to this particular one. So essentially, your map, the number of mappings is your entire candidate space. Can I identify only the good candidates from this entire space, right? So a pictorial way of thinking about here is, so suppose this is your entire space. Every dot here is a possible mapping. But instead of considering every possible mapping, which is n factorial, I want to take only the green maps, right? And compute the graph at a distance by taking the minimum over only this, right? And not everything else. And the question is, how can I do that? How can I identify which are those mappings that actually are the good ones, that contain the potential solutions? Okay. So before we go there, so here is a few important points which we need to recognize here. So the moment I consider a restricted set of mappings, right, we are guaranteed that this is an upper bound to the true graph at a distance. Why? It comes from the definition itself. The definition is it's a minimum across every possible mapping. If I take a subset of the mappings, this is an upper bound. This is important. Why? The reason is now the implication is I no longer need the ground truth data. Why? Because if I can come up with this, let's say I have some way of finding these mappings, right? If I just minimize the upper bound, that means I'm getting close to the true distance, right? So even without knowing what the ground truth is, I can make a proxy optimization problem, which is to minimize this upper bound. And therefore, it allows me to operate without the actual ground truth distance. This is not possible in the neural network scheme because their predictions can either be higher than the ground truth or lower. So you don't know whether it is whether it is smaller or this way. The error can go in either direction. In this case, when you are deriving the value from some few set of actual mappings, you are guaranteed that you can only error on the higher side. And therefore, minimizing how high you go is good enough. Okay. So therefore, the question is, how do I identify this particular mappings? That is the main question. So let us take a look into that. So this is the primary question that we are looking at. And what we do here is we convert this map finding problem into that of bipartite matching. Okay. So what are we doing over here? So the first thing is, given this input graph, let us construct a bipartite graph which is weighted. And this weighted bipartite graph is fully connected. Okay, so what are we doing? So the nodes on this side are the nodes from graph 1, including the dummy nodes that I'm inserting to make it of the same size as the larger graph. The nodes on this side are the nodes from graph G2. Okay? And then we have an edge between every node here to every node over here. It's a fully connected bipartite graph. And we also have some weights. I haven't shown the weights over here, but what should the weights do? The weights should ideally tell you what is the likelihood of this node getting mapped to this particular node, right? As I've said already, right? I think if I map this node to this node, I know that I will incur a distance of 1. Why? Because these two nodes are of the different labels. But then there can be other factors. It's not just mapping this node to the other node, but also the neighborhood and other kind of features also come into the picture. Okay. So now, once I have constructed this particular bipartite graph, then what do? I want to go from a fully connected bipartite graph to a bijection. And once I get a bijection, then I just compute the distance with respect to this particular node mapping. And this gives me a GED upper bound, right? So the crux of the problem is, can I come up with the weights? That is the main problem, right? Because as a function of the weights, when I do bipartite matching, you can use Hungarian algorithm, for example, or some other bipartite matching solvers. So if I come up with the right weights, then this particular map here is going to be hopefully fairly close to the map that minimizes the distance, and therefore, how do I get it? So this is what we are trying to sort of
And you can do this multiple times?
And I can do this multiple times, exactly, as you said. Because each one is an upper bound, I do it multiple times, and that is why I said a small number of mappings. This will give me only one mapping, but I can do it multiple times, get multiple maps. Okay? So therefore, that is the problem, right? How do we get the weights? And the idea here is that we will use LLMs to learn a program that outputs a weight based on the neighborhood topology and the node attributes. Okay? So the LLMs are asked to discover the weights of this particular bipartite graph. Okay. So how do we do this? So so this work, so we are so this the main idea comes from, there's a paper from DeepMind which came in 2023. It's called Fun Search, and now it's called Alpha Evolve, right? So what we do here is we start with before I give you the architecture, just to sort of give you a quick, simple summary of what we do. In a neural network, what do? You initialize a neural network with random weights, right? And then you have an optimizer like Adam, SGD, or something to update the weights based on some particular loss function. Okay? Here, what we are going to do is we are going to start with a random program that generates some random weights, which is going to be very bad. But we are going to give the LLM a feedback how bad this particular program is, and ask the LLM to improve so that the performance of the code improves. Okay? So instead of learning weights, we are learning programs by giving appropriate feedback to the LLM. That is the overall idea. So how do we do that? So we start with the prompt. The prompt, I will explain what the prompt is, but think about the prompt as the initial program that is potentially very bad. Okay? And we ask the LLM that take this prompt, here is our task. We also describe the task that we are trying to solve, and come up with a better program. Okay? So it comes up with some particular program P. And then we do some, maybe the font size is too small, but I'll just read it out. So once this code is generated by the LLM, we do some regular checks that first it should execute. It should not have syntax errors or any kind of errors. That happens. And it terminates within a time limit, because, which is still a hard challenge, an open challenge, we have no way to understand what is the complexity of this code. We don't want the LLM to come up with a problem, with a solution that itself is exponential, right? So we have a hard time limit over here. Time limit is a proxy, again, if you can critique that, but that's what we do, right? And if it passes those filters, then what we do is we use this code to come up with this particular bipartite graph. Okay? So this code comes, here we have a training graph, the graph pairs. We compute the weight matrix using this particular code that it has come. Here is our fully connected bipartite graph. We compute the matching, the bipartite matching over here. We get a one-to-one matching. And we therefore, with this one-to-one matching, we get a distance with respect to, for every graph pair over here. Okay? And this program then goes into our program pool. Okay? By pool, I mean because, as you can see, we will do it over many, many iterations. So every iteration generates a new program, okay? And every program is inserted in this particular pool. We also arrange the pool in terms, there can be many heuristics that you can apply, but think about them as like each island here is a set of programs that are similar in nature. Okay? How do you say which programs are similar? You can purely look at how the performance on the different graphs, graph pairs that you're doing, or you can use other mechanisms also. There are multiple mechanisms that one could use, right? So once you have this particular pool, what we do here is from this particular pool, we will select the K best or B best programs, because B is our budget, the number of mappings that I actually want to consider, right? N factorial is the exhaustive set, but I want a much, much smaller number. Let that number be B. So I take the smallest one, and I compute what is the upper bound of the graph at a distance that I get over here. If that upper bound has not converged based on the previous round, then I will continue to ask the LLM to generate more programs. Okay? And if the upper bound has converged, then I will stop. Okay? So every round, the LLM keeps generating new problems, and we do that. So what goes inside this particular prompt? What goes in this prompt? The prompt has primarily 3 different components. One is the problem description. So here you describe the problem, which in our case is graph at a distance. Then the next one is task specification, which is graph at a distance, but we're trying to specifically get the weights as a function of the graph topology. So it's a more formal definition of the function that it needs to write. Okay? And then the feedback here are the best programs that it has generated in our pool, right? So we are trying to now ask the LLM to improve based on the best programs, right? And this is managed using a genetic evolution algorithm. And therefore, this is the function header that the LLM needs to generate. So we give it the API, and it needs to fill in the body of that particular function. Once this function comes, it goes back into the pool if it satisfies the checks. Okay. So now the question is which programs to select finally in our solution, right? So the idea here is we don't want to select the B best performing programs, because we are taking the minimum over all of them, right? So we want the set that jointly does the best, rather than just independently selecting the B programs that does the best. Okay. So how do we handle that? If you first, before you go to handle that, you want to sort of write down the formulation that you have here. I have D programs in my pool, and I want to select the subset that the minimum over this subset is closest to is as small as possible. We don't have ground truth supervision. We want to just minimize that, right? So therefore, we want to choose a complementary set of problems, because I may have two set of programs that are minimizing well in the same set of graphs and doing very poorly in another set of graphs. We rather want programs that does well. One program does well on this distribution, and another program does well on another distribution, right? So therefore, this is a combinatorial problem in itself. So this is also an NP-hard problem if you think about it. But fortunately, it's a little bit better characterized. This is monotonic and submodular. You can prove that, and therefore we use a greedy hill climbing algorithm to sort of solve this. Okay, I will skip the details like how, but it's fairly standard in when you have monotonic and submodular functions. So that is roughly the overview of the architecture that we follow here. More details are there in the paper, and I'll go over into the results. Right. So here is the different data sets that we have looked into. It tells you the graph sizes, the domain, and all these other details. And we looked at two different metrics primarily. One is the error, the RMSE, and the other is the exact match ratio. That is for how many graph pairs we're able to get the ground truth edit distance. Okay. So here is the results. So these are the non-neural heuristics. These are the best neural heuristics that you have, and this is what we came up with. There are two versions that we did. One is called GRAIL, which is trained on each dataset separately. Okay. The other one is called GRAIL mix. What we do is we take an equal proportion of graphs from each of these dataset, okay, and we train them jointly. And the same set of programs is now used on every other dataset. So we don't do a dataset specific learning anymore. And what you can see here across many, so the colors encode the accuracy. That the deepest one is the most accurate, and then the next deepest one is the second, and so on. And what we see is that we are consistently, very competitive across all the different non-neural and neural heuristics, right? So I think the performance was actually, to summarize, was very, very promising here. We also looked at the exact match ratio, that is how often we got it correct. And this is where we are even better, right? I mean, you can see that for some data sets, we are getting it correct like 80% or almost 0.99% over here. Some data sets are harder. Here it is not, it is harder. But in general, we are doing fairly well in getting the exact distance, right? So those are the positive things, right? And the part that excites us more. So for example, if I use the functions this is not GRAIL mix, this is the GRAIL. Like if I use the program generated by training on AIDS, and if I use it on other data sets, right? You can see over the other data sets. The diagonals tell you when you train on the same data set and test on the same data set, and this is when you train on a different data set and you test on it. The performance is not super bad, which you see with neural networks, right? That the performance really breaks, but that is not the case over here. They roughly remain, relatively decent. So it is kind of like a foundational set of functions that works well across data sets. And the good thing, you just have a bunch of Python programs and you just run them. You don't have to train them at all, right? So what do you get here? What kind of functions are you generating here? Typically they're looking at topology. They're looking at node attributes. And the feature distribution in the node as well as in the neighborhoods and so on. So many of the functions are looking at different combinations of that and different kinds of way to aggregate them. right? So this paper was published in ICML, as I said. So the paper is available if you want the code. Everything is already there, right? And I think I have covered this kind of things in general. Because I have less time, I'll just quickly mention that we looked at it for graph at a distance, which is a specific algorithm. But in general, this is the sort of recent works that are looking at algorithm discovery, or automated heuristic discovery, right? So this is not yet as mature an area as some of the other areas of LLMs. For example, LLMs for mathematical reasoning or something, where tons of papers are coming out every conference. But there are many things to do, particularly if you're in academia. We cannot keep making LLM calls because these are expensive. We burned like $1,000 to write that particular paper, right? And if you're now trying to cater to a larger number of algorithms, these things are expensive. So, and which LLM to use? Do I use the cheaper LLMs that are less powerful as a reasoning model versus the more expensive ones, right? How do you balance them? When do you use them? Because it's an iterative sequential process, right? So this is an open problem. How do I make them more sample efficient? And how to design the prompts? These are all kind of open problems. And have not really matured as such at this time. And the North Star, I would say at this time is, if you just ask the LLM to directly solve the particular problem, it does not do a good job. If I ask the LLM, okay, here are 2 graphs, tell me, write a program to solve graph at a distance, it does poorly. What helps is when you break it down into the small subproblems. Graph, bipartite matching, come up with the weights, then solve it. It's very important. That means there's still a lot of human intuition and intervention that is still going into the picture. So we haven't really solved what we are really trying to solve. So therefore, the real challenge, which is the North Star in this domain, is that I have a prompt where I describe the algorithm, here is an LLM, and it generates the code without any human intervention, right? So can I identify how to break it? What are the different heuristics to sort of really use, right? This is open. I mean, we don't have a solution here yet, right? But this is, therefore, fertile grounds for more research. I will just end there and just want to sort of thank my collaborators and students, right? I mean, much of the work and coding was done by them. And if there are more questions, I would be sort of happy to take those, yeah.
Thank you. So you said that when you do the last slide that you showed, fully LLM-generated code for the full problem, graph at a distance, it works worse. And it is probably even worse than the other neural baselines.
Yes. Yeah.
What about generalization? Is it still bad at generalization? Do you have those type of matrices? The previous slide, I think. This matrix for that one?
No, we don't have this matrix for that one. The reason is because it was already fairly poor in just solving it on the same data set itself, right? So we did not explore that we do it. My guess is it will remain perhaps equally poor for all of them, because if it is giving you noise, the noise
but
does not...
But is it noise? Like, isn't it better than some of the old baselines?
Well, it may be, but I think if you look at them, right, like okay, so it's definitely way worse than many of the neural baselines. It may be better than some of the non-neural ones.
But if you do neural generalization, the matrix for neural ones, that would explode, right?
Okay. That would explode. That may explode. So you are saying that this may generalize better than the neural ones, which is possible, because which is possible. We haven't done that, but your intuition may be correct over there. Yeah.
I see. And did you use Gemini or ChatGPT?
We used Gemini, but not their most expensive one. We could not afford to make so many calls. The exact version, I hope it was listed. I think it was Gemini Flash Pro, or it should be. It's there definitely in the paper.
Maybe now it's possible to use, I don't know, the latest Quen or whatever, self-deployed, right? So that it's not infinitely expensive.
Yeah, I think, so I think we could also use any of the open weight models like Llama or Mistral. So Those could also be used. We haven't tried them yet, but I think now the current project, we are actually basically looking at, do you really need the expensive models?
Yeah.
Or do you need the
because
simpler
I mean, you can ask 10 times more the stupid model.
Exactly. So that is the problem that we are trying to sort of really understand. And hopefully a benchmarking study or something of that sort will come out. But that's the objective, yeah.
Great. Do we have questions? Yeah.
I wonder if you studied like all possible solutions that LLMs generate, because like generally if you generate code with LLM, sometimes it just repeats the solutions.
Absolutely. So that's again, so we are also looking at the diversity of the solutions. Okay, and I think only one paper in the current one that explicitly tried to bias the LLM for generating diverse solutions. We have looked at it. Our solutions are not very diverse. At least to us, it does not look very diverse. I mean, they are kind of similar. Although, as I said, when we want to jointly identify the programs that makes them as good as possible, it does have an effect. But there also, there's an aggregation step, right? So this step over here can sometimes be arbitrary. I mean, it comes up again with a particular function. So I think it is. The combinatorial effect comes purely based on the kind of these arbitrary functions that it is coming up with. But this part, where it is doing the feature aggregation, that is not very diverse. That is fairly similar. We tried telling the LLM that why don't you also try use these features. The problem with that is then the LLMs only starts using those features only, and it stops thinking on its own. So how do you balance in giving feedback to the LLM versus letting the LLM completely come up with its own choice? That's an open. I mean, I think we actually need to sort of optimize that particular aspect. And diversity is actually very important because ultimately we want the solutions to be passed on to humans, right? Even if I don't get the best solution, if I come up with a new way of solving a particular problem, that itself can be a very important discovery. So right now, we did not see too much diversity in the features, and potentially, but you could potentially reward the LLM to go towards more diverse solutions.
Did you try beam search to to improve the diversity with?
No, in this one we haven't tried anything, but I think people have tried tree search-based ideas, MCTS and those kind of ideas. I think to aid diversity or having. So when you say like right now, what do? We get a program, and we check what is the performance of that, right? You could also score a particular program based on how diverse it is from the existing particular pool.
Oh, okay, yeah.
So that can also be done. So diversity can be handled from multiple angles, right? But there is only one paper that I've looked at diversity explicitly.
I see. The way we do it, when we prompt the model to generate new, in our case, molecules, in your case, programs, at that point, you can ask for multiple solutions and do beam search, so that guarantees that you have at least different, but it does not mean really diverse. It could be very similar and different. So it's confusing. But yeah, that could.
The question is, what is diversity? That you also have to think, right? So diversity in terms of logical interpretation, or diversity in terms of the molecules or the distributions where it is doing well. Right? If you're looking at a distribution, it's easier to sort of map that to a scoring function. But if you're looking at logical diversity, then you have to sort of understand what the program is doing, and then kind of do something, right? So there are some works where the feedback to the LLM is not just the program, but they ask the LLM itself to also convert and generate comments that summarizes what the program is doing.
Oh, okay.
And then that also is given as a feedback. And apparently they claim that improves the performance. So there is at least one paper that does that, right? So those kind of ideas could also be used for the diversity in the LLM space. I think this one, verbal feedback. So which uses LLM comments to also go along with the prompt. So those things. But what is diversity? I think typically we are looking at diversity in the logical space rather than diversity from a performance perspective.
I see. Yeah. One more thing. Do you have generalization across number of?
Yes, that works fairly well. That doesn't, because most of the things that you see over here,
That's crazy.
Yeah, the number of nodes is not a problem. I think because of it, often it just looks at the one hop or two hop neighborhood and then normalizes that in some particular way, like the average or something. So I don't think the generalizability with number of nodes is not a big concern, I think. At least for graph-edit distance. I cannot speak yet for the other ones, yeah.
Did you look at how the models perform to the different types of graphs? Let's say if you have a linear graph, let's say text at the distance, does it perform better to other kinds of graphs that are highly topologically complex? Is there such a sort of, is it harder for them to do the hard graphs, or is it just all the same?
No, the distribution of the graph does matter, right? So for example, but we don't have a clear way to sort of say why or when it does well, because then we have to sort of really look at the program. But to give you some picture here, so if you see, the performance is really good in Linux and IMDb over here. These are both unlabeled graphs, okay? The error here is 0.13 and 0.55, and IMDb is it's a fairly large graph. I think the number of edges is like 80 or something, way larger than the molecules. And it does less well on the molecular data sets, and this is a function call graph of software repositories, right? So labels make the edit distance computations more challenging, because then you have to look at the label diversity and whether you're mapping the node with the correct label. There is no more heterogeneity in the neighborhood that you have to sort of summarize into these features, right? So if the graph distribution has more heterogeneity, right, I think it's more challenging, right? And we clearly see that signal for labels, but there may be structural, like as you said, linear graphs versus more complex graphs, right? We haven't done that study systematically, but I would guess that there would be some correlation in terms of how well it does with respect to the graph distribution that you have.
Thanks.
Thank you very much for the talk. It looks like your approach is quite general. Have you tried to apply it to other NP-hard problems or just some other problems?
Yes, so I think that's what I said. So it's general in terms of how the LLM evolution is happening. It's not generic in terms of how the problem is being broken up into smaller sub-problems, right? So the LLM evolution, we have tried this on other problems like traveling salesman and I think CAPSAT problem and some other NP-hard problems. But that is kind of what we use the Google's fun search platform, and we kind of developed from that. So that's what the first fun search paper did, which is look at a bunch of generic problems. So this same pipeline will work for other NP-hard problems also. But I think the challenge lies in what is the prompt structure, because the prompt structure is very specific to that particular problem. So the evolution part generalizes well, reasonably well, but the prompt does not generalize well. There is a lot of human intervention. It's like feature engineering for algorithm discovery. That is what we potentially may want to automate in the future.
Yeah, splitting the problem into these two sections is probably the most expensive part, right? Like it's...
Yeah, absolutely.
I see. More questions?
We haven't, but we are discussing, like, can we train different LLM agents to do those different kind of tasks, right? I think there is promise in the idea, right? Because if you search, for example, what are the approximation ideas for graph-edit distance? Bipartite matching is there, right? So if you have specific LLM agents trained to sort of, okay, here's a complex problem, how could you potentially break it down into simpler problems? If you ask this question to GPT or any of the LLMs, they may give you interesting ideas, right? But how to do that in an automated manner, we haven't done that yet, but I think it is possible. So you could have the specific agents that take different components of this and automatically come up with the prompt. As of now, it does not exist, but it's an open area. Can you repeat the question? I did not get that.
Did you try to use Cursor or others to do the same stuff with the same prompt?
No, I think we just use the Gemini Flash Pro. That's it, right? But if you use some other, like a Cursor or some of the other things you're talking about, or?
Yeah. Talking about agents that actually generate the code, like a version of the agent.
Right. No, we haven't tried those things. Yeah, we haven't tried those things. Yeah.